Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
And it is not that types of geometries alone. There is something called dislocation loops, which is more realistic. And suppose if you see that a crystal contains a dislocation loop like this, how do we understand this? Suppose this is a glide plane. Glide plane we know now where the dislocation moves easily. So this is a shear stress direction. And suppose this is a loop. And then how do we understand this Burgers vector here? The Burgers vector is marked like this. So at least one point you can think of, since we know the Burgers vector's orientation with respect to dislocation line, we will be able to clearly say that, okay, suppose if it is parallel to this could be a screw character, and if it is perpendicular to this, B could be an edge character, and in between we know the mixed character. So that is how we should understand this loop. Okay. Suppose if the completely the loop is generated inside this crystal like this crystal unit. Once this the unit the dislocation loop comes out of this unit cell, then it will leave the slip line like this, a slipped region in the crystal like this. Of course, that is a glide plane. So a dislocation loop and an offset produced by action of shear stress tau upon loop, what is shown here. Okay. See, the other schematic what is shown here will give you much more again clarity in terms of, suppose you imagine that a huge chunk of a crystal unit has been taken out from the larger crystal, something similar to this, which has got a dislocation loop in it. And how do we understand this loop with respect to the screw and edge character? That's what is shown here. It's the same idea, but as we have done with the previous slides, like we have taken some extra schematic to describe and get more clarity. Similarly, we can do that here. So what is shown here, this is a slip region inside the crystal unit, and this is the cutout unit from there, which is already slipped, which is exhibiting a screw character as well as edge character, and somewhere in between a mixed character. That we know what to do, right? So now what is shown here is the loop in the opposite ends will have the dislocations of opposite sign. That is one important character. So I just mentioned here, it's about whether it is a screw or edge with respect to B orientation. That's what I just mentioned. But within that edge dislocation, if these opposite sides will have opposite signs. Okay, so this is positive edge dislocation, this is negative edge dislocation. So similarly, this is positive screw dislocation, this is negative screw dislocation. And we have to make sure that, okay, in terms of geometrical understanding, you just look at this the clockwise Burgers circuit, which shows the Burgers vector B, right? B is here. This is a B, and it should be the same Burgers vector in the other side also. Okay. Even if you do it in a anti-clockwise, the Burgers vectors of both these sides should be similar. So these are some of the simple points, but important points you have to remember if you want to keep the track of dislocation line, orientation, Burgers vector, and so on. Okay, so that is about the dislocation loop description. So now let us spend some time on Burgers vectors. Okay, which is also very important. How do we mark this circuit? So this is the lattice which has got a dislocation. Extra half plane is inserted here. Then I have the dislocation core here, which is marked by this. And here it is positive dislocation. If it is inverse symbol of this, it will be a negative. The dislocation line is perpendicular to this, which is going inside the, perpendicular to this plane. So how do we mark, and what is the rule for this making a circuit? Dislocations are characterized by Burgers vector. Consider an atom-to-atom circuit in the figure that would close on itself if made in a perfect crystal. Suppose you start counting. Suppose you leave this core, first line, and go to the second line. Start counting the displacement. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That's it. And then this particular gap, it is failing to close. So that means this is the that is a defect, right? That is a measure of defect, which is here it is a Burgers vector or failure gap, you can whatever you may call it. So wherever if you do it the same thing in a perfect crystal, it will close. So if it is around the dislocation, it will not close. Yeah. The closure failure is the Burgers vector denoted by B. The Burgers vector can be considered as slip vector because its direction is the slip direction and its magnitude is the magnitude of slip displacement caused by its movement of the dislocation. So this is very important because Burgers vector describes the the slip direction as well as its magnitude of slip displacement. That is why it is very important. A dislocation may wander through a crystal with its orientation changing from place to place, but its Burgers vector is the same everywhere. This is something you have to remember. This is exactly we have just shown in the previous slide. Whether it is looking at a cutout crystal block, we have measured the B, but that is same everywhere. Whether you measure it clockwise, anti-clockwise, whether you measure in a screw dislocation side or edge dislocation side or a mixed dislocation side, the magnitude is same. Okay. If the dislocation branches into two dislocations, the sum of the Burgers vectors of the branches equals its Burgers vector. So this point we will just we can qualify after a few slides. We will look at it later. So there is a simple notation system for describing the magnitude and direction of Burgers vector of a dislocation. The direction is indicated by the direction indices and the magnitude by a scalar preceding the direction. So how to give a kind of notation system? Okay, so this is a kind of notation system. For example, if the B is given like this, A by 3 times 2 bar 1 direction in a cubic crystal means that the Burgers has components of 2A by 3 minus A by 3 and A by 3 along the 100, 010 and 001 directions respectively, where A is the lattice parameter. Very important. Don't get confused with this symbolism. A, lattice parameter, and you know how to mark a direction in a crystal. So planes and Miller indices we would have seen it, right? So it is the same thing. So direction and the magnitude is given. Okay. So all the Burgers vectors will have this kind of notation. How much magnitude in terms of the lattice parameter and what is the direction. Its magnitude is mod b, so which is you can square and square root of this, the direction components. In this case, it is a times square root of 6 by 3. Okay. A dislocation in an FCC crystal corresponding to full slip displacement that restores the lattice would have the Burgers vector a by 2 in 1, 1, 0 direction. In this case, the magnitude is a times square root of 2 by 2. Suppose what is mentioned in this point is, suppose in an FCC crystal has got a slip displacement. It has slipped. To restore that slip region, then the Burgers vector has to move this amount in this direction. Okay, that's what it says. Okay, how do we see this dislocations? Okay, dislocations are visible in transmission electron micrographs. Okay, so what you are seeing here is a bright field transmission electron micrograph. Typically, the dislocations are visualized in this manner with a dark contrast, what it exhibits, okay. Dark lines. Okay, this is how it looks like, at least. If you want to get into why it appearing dark and how you are seeing this is a loop and other things, it requires much more knowledge of microscopy and diffraction contrast theory and so on. Probably you can just take a help of some characterization course to get into the details. But this is just an example how it in reality, what do you see? How do you see? Because we just said that edge, screw and loop, and this doesn't give that kind of a feeling. It gives much more chaotic, right? So to get into this kind of, suppose if you want to analyze some of this lines, like whether it is a loop or suppose whether it is an edge character or screw character, and this requires a further analysis, but it can be done. Okay, that is a different field itself, analysis of a dislocation in TEM. Okay, so for time being, it just the message here is we can visualize a dislocation in a TEM to understand their behavior and, or I mean, at least look at their morphology, density, how much, where it is formed, whether it is formed near grain boundaries, whether it is formed near any second phase particles or interface boundaries. It's very useful, at least, right? Whether you involve yourself in analysis of this location, that's a different question. But at least we are able to see them. Okay, let us summarize this geometry of dislocation. They are line defects. They are one-dimensional defects around which atoms are misaligned. A dislocation may be considered to have, in general, two components, edge component and a screw component. The geometry of the lattice irregularities described by these two components, which may be treated as two simple kinds of dislocations, shown in the figure. And one property of dislocation is its Burgers vector, V, which describes both the magnitude and the direction of the slip. The Burgers vector of a pure edge dislocation is perpendicular to the dislocation line. That of the pure dislocation is parallel to the dislocation line, and the Burgers vector of the hybrid dislocation makes an angle with the dislocation line. When three dislocations meet at a point called node in a crystal, the sum of their Burgers vectors is B1 plus B2 plus B3 is equal to 0. So this particular point we will see it as we move along. In a nutshell, this is a complete description of at least the geometrical nature of this dislocation, how they look like. Okay, so now we can move on to next topic, energy of dislocation. Why are we bothered about this energy of dislocation? Okay, dislocations are not thermodynamically stable. Their presence always increases the free energy of this crystal. So now we are giving more information. The presence of dislocation increases the free energy of the crystal. Consideration of the energy of the dislocations can be used to explain the following. Why moving a dislocation requires a lower stress than moving a whole atom plane the same distance? Why crystalline material becomes harder with increasing strain? Okay. So this is the first two questions are quite relevant to what we have just seen, right? The theoretical estimation of bond strength, okay, which is very high. And suppose if we say that dislocation is responsible for observing the lower strength and so on, but unless we understand the energy of dislocation itself, we cannot explain the other concept, right? So that's why understanding of energy is important. And again, why crystalline material becomes harder with increasing strain? Increasing strain means we are multiplying the dislocation in this crystal system. And multiplying the dislocation in the crystal system, it will do so many other things, and the system will become complicated, and the energy always going to get increased. So that's why we are thinking about the energy. Why annealing and recrystallization soften the material? Okay. So increasing the strain increases the dislocation. It gives a clue, right? Increasing the strain increases the dislocation density. Annealing and recrystallization is going to reduce them. So kind of, but we don't know. Why low angle grain boundaries form and are reasonably stable? See, the first statement we say that dislocations are not thermodynamically stable, but here we say that even though it is classified thermodynamically not stable, in certain geometrical positions in a real-time crystals, a typical low angle grain boundaries formed by these defects. We will see them, how it forms and why it forms and so on. And the energy concept really helps there. And why dispersion and precipitation hardening raise the yield stress of crystals. This is another important aspect, very useful in strengthening mechanisms or real-time material development and heat treatment and so on. The dispersion and precipitation hardening has got a close connection with the dislocation and its energy. And finally, why dislocations in FCC crystals break up into into partial dislocations, and why edge pits indicate the presence of dislocations. So we will see in the future slides, and dislocation can get dissociation into two dislocations, right? So why it happens, that also will be addressed in terms of energy. energy consideration. Okay. So you see, several questions can be nicely addressed by the dislocation and its energy. Okay. So we will slowly get into this. Okay, I just want to tell you, since I'm just flipping the slides, I'm going, I may go very fast. In normal circumstances, when we do with, a blackboard and a chalk, the information and what it transmits to you and how much you absorb will be much slower. Since it's a PPT mode, it may look all going very fast, and if you don't be conscious of this factor, you will also get all these concepts will get evaporated from your mind so fast. So do pay attention to this aspect. It is PPT presentation is not a really a good way of teaching, and at least this situation situation teaching mode, this is one constraint. So stop everywhere and then don't go very fast. Go slow and then think about it, and then slowly prepare your personal notes and then try to learn. And you can always interact with us if you have any doubts. Okay. So now we are going to look at the estimation of energy of a dislocation. So what do we do? To estimate the energy of a dislocation, we can consider a cylindrical crystal of length L with a screw dislocation of Burgers vectors B along its axis. So we are going to consider this kind of a geometry. So this is a cylindrical crystal, and this is the screw dislocation as I just demonstrated in the previous slide. The Burgers vector is B here. The radius of the cylinder is R. The length is L. And what is shown here is, just if you open this cylinder, it will be like this. It will be a sheet like this. And this particular geometry is very familiar to you. What is this? We described in the beginning, some of our previous chapters, it's a shear displacement, right? The shear displacement. So what is that we are going to see? B and 2 pi R. That is because of the cylindrical geometry, and this is L. So the elastic shear strain gamma in a thin annular section of radius R and the thickness dr is gamma is equal to B by 2 pi R. So now you have enough background to understand this simple calculation of shear strain gamma and how it comes, right? So we don't have to spend more time on this now. And where B is the Burgers vector here, but we are interested in the magnitude. So what we are interested in? We are interested in the energy per unit volume, that is dE by dV of the thin annular region is then given by dE by dV is equal to half tau gamma. This expression also quite familiar to you. We may not have used exactly dE by dV, but then you see that half tau gamma. If you go back to the initial elasticity theory, we have seen all this. Okay. So gamma, you substitute that whatever we have seen earlier, then you get this expression dE by dV, right? Where G is the elastic shear modulus, the volume of the annular ring is dV is equal to 2 pi R L dr, and you can write dE is equal to Lg B square by 4 pi times dr by R. Okay. The strain energy resulting from the presence of this dislocation may be computed by integrating from some lower limit R naught to some upper limit R. You see, we are looking at the cylindrical annular system, right? So, but we have not fixed the R. So, to calculate the strain energy resulting from this kind of a dislocation, the R can be varied from R naught to capital R. So, that is the idea. So, for that, we are going to integrate this expression, that is E is equal to integral over R naught to capital R L GB square by 4 pi times dr by dr, so dr by R, which is equal to L GB square by 4 pi ln R by capital R by small r plus E naught. So this is a simple integration. If the limits of either R naught is equal to 0 or R is equal to infinity are chosen, the integral is infinite, which is clearly unrealistic. So either you cannot, either you choose R naught or R as a 0, then the integral becomes unrealistic. Okay. The difficulty with choosing R naught is equal to 0 is that Hooke's law is not valid for the high strain at the dislocation core. Okay, very important point we have reached. Okay, the very reason I have just moved to this topic of dislocation before going to anything else is the energy system and the stress field around the dislocation, everything is dealt with elasticity theory. Since we have just looked at all the concepts or brushed up all the elasticity theory, I thought it'd be very easy to just describe the dislocation before you forget everything in total. Okay, so the whole stress field around dislocations are explained by elasticity theory only. Okay, so if you take R naught is equal to 0, then the Hooke's law is not going to be valid. Okay, because of the very high strain at the core. Because we are talking about elastic behavior. The core of the dislocation need not follow the elasticity theory concepts. That's the idea. The value capital R is equal to infinity is also unrealistic because at large values of strain field of the dislocation is cancelled by those of the other dislocations. We are going to qualify all these statements one by one. So it has been shown that if R naught is taken as B, the real strain energy inside the core E naught is only a small fraction of total energy and can be neglected. Since the energy is relatively insensitive to R by R, the ratio used is usually ln capital R by R naught, which is equal to 4 pi within the limits of the approximations made. Then the energy of the screw dislocation is given as E is equal to approximately equal to L GB square. So finally, we with all these assumptions, we got one expression of energy of a screw dislocation. E is equal to L GB square. So G is a constant, L is geometry anyway. So what is the message? The energy is proportional to square of the Burgers vector. This you have to remember. That is what we have shown in the beginning, but this is what we have finally arrived at also. So what I'm now showing here is two schematic. One is edge dislocation and the screw dislocation. And what is shown, there is a shadow behind, right? Behind this three-dimensional schematic, there is a shadow. We kind of try to show the stress field around this dislocation. The energy of a dislocation, edge dislocation is given by approximately by E is equal to 1 by 1 minus mu times L GB square by 4 pi ln R by R naught plus E naught, which is equal to L GB square by 1 minus mu. See, all of you now must get alerted. The moment you change from screw dislocation to edge dislocation, the modulus part is changing to not just G, it is G by 1 minus U. So you just recall, we have derived this. Where do you get 1 minus U term in elasticity theory? We have derived a lot of small derivations, right? Especially in the elastic stress strain relations. If you go back and see, we have just derived this 1 minus U term. Where does it come? You look at what is the modulus given for plane stress problem and a plane strain problem. Okay, very important. So the moment you go to the plane strain problem, then this kind of 1 minus U terms comes in a elasticity theory. So something like that. We are not getting into the details, but I'm just giving you a clue. Right? So when you move from screw dislocation to edge dislocation expressions, you will always see that this 1 by 1 minus mu term comes in the edge dislocation. Okay. So you can just imagine that, how it would have got inserted. That is because you are now considering the state of stress as a plane problem, especially a plane strain problem. Then the 1 minus mu term comes. So if you understand all these subtle differences, then you don't have to worry about all these mathematical terms. It's very easy to look at it. Where the mu is the Poisson's ratio, if mu is 1 by 3, the energy of edge dislocation is about 3 by 2 that of the screw dislocation of the same line. Since the energy of the edge and screw dislocation is proportional to B square, the most stable dislocations are those with the minimum Burgers vector, which is those in the closed pack direction. So this is very important information again. Okay, it is talking about stability. The most stable dislocations are those with a minimum Burgers vector. The equations above also show that the energy of a dislocation is proportional to its length. Yes, E is equal to L times GB square. That's what we have seen, right? So just as the surface energy is equivalent to surface tension, a line energy is equivalent to line tension. This is kind of analogy. Okay. Thus, a curved dislocation will have a line tension T, a vector acting along the line. So we can write it like this: T is equal to rate of change of energy or change of energy per unit length is equal to GB square. Line tension. We will use this term when we talk about dislocation interactions and dislocation interact with obstacles. These concepts will go a long way when we discuss about strengthening mechanisms and so on. Okay. So it is good that we get familiar with all these terms right at the beginning. The line tension. So this is a stress field behind this two dislocations. Again, when you talk about stress, now so far we have just seen the energy of dislocations. Now we are going to move on to stress fields, which is again very interesting, and it will be very you will be very happy to see that most of the expression you are already familiar with, right? Because they are all treated by elasticity theory. So I think we'll stop here and we'll move on to the next topic in the next class. Thank you.